Good morning and welcome back to the second webinar of FOGTEC fire protection about rolling stock in fire protection in rolling stock. I was really happy again to see that friends and partners from all over the world joined also this morning our session, in this case about RAMS and lifecycle costing. My name is Roger Dirksmeyer. I'm the Managing Director of FOGTEC Fire Protection and would like to give a very short introduction as I saw that most of you also joined last week this session, so I will not repeat too much, but just to give the ones which joined not last week, I would like to give a very short overview. First of all, about our schedule in general. Last week, as already mentioned, we did a presentation about general information and short case studies in fire protection in rolling stock, where our colleagues René and Claudio gave the introduction and the presentation. Today, we are with Jonathan and Gail for the topics of RAMS LCC, and in 3 weeks, we will give a special session on 3 different times during the day, covering different regions of the world where fire protection and rolling stock is an important topic. Few words about FOGTEC, which is an owner-managed company established in 1997. The headquarters is located in Cologne. We have some subsidiaries and offices in Mumbai, Shanghai, and Austria. And with a team of mainly engineers, and more than 50 partners worldwide, we're covering the business and the support for fire protection solutions, and here today, especially about fire protection rolling stock all over the world in a global approach. They are mainly experts in engineering and design of complex firefighting and fire detection solutions to meet the requirements of our customers. The service including also the consulting and development of specific protection solutions, and which are validated in full-scale fire tests. Within the last 20 years, FOGTEC became in its market one of the worldwide market leaders. And the 3 business units FOGTEC is mainly serving in are the fixed systems, which are covering building and industrial applications, the rail systems covering everything what is running on track, and the tunnel systems, which covers all underground infrastructure, mainly tunnels for road and rail, was one of our most important references, which you can see here on the picture in the background, the Eurotunnel. But today we will speak about the FOGTEC Rail Systems Department, which is a world market leader for active fire protection solutions in rolling stock applications and is supplying to most of the OEMs all over the world. And this is the time where I will hand over to my colleague Gail, who starts with the topics of RAMS and lifecycle costing. Thank you very much from my side, and Gail, it's yours.
Thank you, Roger, for introduction. And also from my side, I would like to warmly welcome you to this webinar session in the critical situation of today, where we have not possibility to meet face-to-face, where we need to find an alternative solution. And I'm Gail Wissen, area sales manager at FOGTEC, and with my colleague Jonathan Redding today, we will present some topics about RAMS and LCC issues applied for fire protection solution. What I want to point out before we start is that we are not going to perform any RAMS or LCC study now together. We will more get an applied point of view for our products, our fire protection solutions. Before we start deeply inside RAMS and LCC analysis, I just wanted to show you an example of an application study of a typical system architecture that we can have, where usually we have one central unit located everywhere in the train, ring bus architecture that connects all bus participants to the central units, and we may have several smoke detector or other kind of detector that are located in different area of the train. In normal operation, what happens, the smoke detectors and all bus participants, they communicate at any time to the central unit over a ring bus architecture. Means we have therefore a redundancy, as Jonathan will present afterwards. And when a fire occurs, let's for example here in the passenger area, a first detector will react. At this stage, we only have a pre-alarm status and no alarm and no activation of any firefighting solution. Only when a second detector comes in alarm stage, then the alarm is confirmed and the procedure will be followed. Then the information is sent to a central unit. Central unit gives the order to the cylinder system to activate, and the release of the, here in this example, the water mist will occur only in the detected area. So we are not going to float the complete vehicle, but only in the section where the fire was detected. In a typical way, if it's a technical area where we can use smoke, temperature, gas, or any combination of detectors inside, then in a similar way, it communicates anytime over the ring bus architecture to the central unit. And when the fire occurs, the central unit gives the order to the fire extinguishing system, here in this example, aerosol, to activate in the dedicated cubicle. So this was just some basics about how the system is working. Now we will step inside the RAMS details, and I will speak a bit about reliability. Reliability, it starts at the early design phase. And first of all, we need also to know which is the mission profile, what kind of application the system will be used. And then according to this, we have to define each failure rates of the different components. For electric or electronic components, it can be based on inherent failure rates, whereas for mechanical part, usually it is a quantitative analysis of fail data if available. And then you probably already know this bathtube curve, where at the beginning in commissioning phase, of course, you're debugging the system and the failure rates decrease. Then over the normal operation lifetime, we have an almost constant failure rates. And at the end of life of the product, due to the usage over the years, the failure rates increase again. Then in the second step, the reliability is based on analytical calculation like FMECA, using the MTBF values of the single components. In the second step, we go inside a testability analysis, where we have here on the right an example from a previous system we did some years ago, when you see the sum of all failure rates, 100%, and at the end, the sum of T2 rated failure rates. T2 rated means that it leads to a stop of the vehicle from the mission or to a delay of more than 5 minutes. So only 2% of the overall faults may lead to a T2 failure. In the same way, we have also the possibility using the testability analysis to detect and to define which kind of failure are detectable over maintenance, preventive or corrective, or directly by itself by the system. Here in this application case, we are almost possible to detect 98% of all failures possible on the system. In the next step, a fault tree analysis, so-called FTA, can be done, defining the undesired event and definition of the functional block diagram, as you can see here. So each block is defined with each failure rates, and then the tree is built to define for the overall function the risk of having a failure. All this is not new. It is based on normative requirements like EN 50126, and we apply, of course, the mandatory rules here. The reliability assessment is done at two levels. First, at component level, as mentioned before, we need to choose the material in the right way, knowing their failure mode and related failure rates, to be sure that we can meet the reliability target expected by customer. In parallel, we have also to validate all single components for the requested condition, in particular for railway application, like in Europe, we use the EN 15155 for all types of shock vibration, climatic condition, voltage, and so on. So this is, of course, stronger conditions that we may have, for example, for building technology. In a second step, we go into the system level. System level needs, first of all, to validate the project processes. For example, who is allowed to write a document, who is allowed to review it, who is allowed to give it free, to make sure that we have our at least 4 6 eyes principle applicable. In the second step, we go inside the software assessment, like SIL2 assessment that we will speak about later on, according in EN 50657. And at the end, we reach the complete system assessment, which is finally the only document that the customer receives at the end, but there is a lot of steps behind and lots of documentation to be produced in advance. And we will speak about also later on in this webinar. From this time, I would like to hand over to Jonathan Redding. He will present to you the part of availability and maintainability. So Jonathan, the floor is yours.
Thank you, Gael, and good morning, everyone. I would like to introduce myself. My name is Jonathan Redding, and I'm also an area sales manager at FOGTEC Rail. And the first part I would like to talk about is the next in the line of RAMS, which is the letter A, and availability. So maybe we first start off, what do we understand by availability? Well, simply said, it could be say, will the fire protection system be working and be available when I need it? That is when the train is in service. So all this depends on the reliability, as Gael has just explained, and also the design of the system and whether or not failures can be detected to avoid unscheduled downtime. So as I said, system design is very important. And as we already said, selecting reliable components for the railway environment is important. That's why we do the testing of all the components on shock vibration and so on. But one of the main issues on availability is to try and avoid or eliminate single points of failure. These are failures which will cause the system to be unavailable. So by avoiding these, we can then say, even though a failure occurs, the system is still available. One example of this, as just mentioned, is the idea of using a ring bus. So here we have a schematic of a system where the central control unit will have a ring bus attached, which will then to which all the components are connected. Now this bus will continue through the train and loop round and come back to the CPU. So in the case of any part of this wiring, which is a physical wiring with connectors which go between the vehicles as well, should that be broken in any way, the communication will still continue down the other side of the bus. So this way, even though we have a failure it will not affect the system. This is an important feature. Now, complete redundancy is not always feasible. I mean, the best way would to have everything doubled in the system. So if one point would fail, it would continue with the other system. But this would be far too expensive and also have a lot of cost involved. So we look into ways of reducing the single points of failure with other methods. And just as an example of another method we use, in a fire suppression system with water mist, we use nitrogen cylinders under pressure as a propellant to displace the water into the suppression system through the nozzles. Now, instead of using just one nitrogen cylinder, we can one large nitrogen cylinder, we can use two smaller ones. And now these are activated by a valve, which is opened with an electric signal. To make this a redundant system, we can have these valves are designed so that they can be opened electrically or pneumatically. And the valves are so configured that when one valve opens electrically, it will send the pneumatic through the pressure to open the other valve. So each valve, in effect, will open twice. So this way we have a redundancy built in to a system without really doubling the complete system. Now the other way is obviously doubling up the number of components. The CPU is a system which is quite often done as a separate, as two CPUs to be completely redundant. This is a possibility, but not always necessary. Now, the other point on availability is reducing unscheduled downtime. This depends on the maintenance, so it's a matter of detecting faults and repairing them quickly, which brings me on to the next point, which is the maintainability of a system. Maintainability is, well, basically the ease of how easy is it to maintain a system. So what we will look into is which parts of the system, what has to be maintained on a fire protection system. And there are different sort of levels of maintenance: preventive maintenance, predictive maintenance, corrective maintenance. And we will just look into how we can combine these to minimize the costs of maintenance. So going back to that illustration that Gail showed, which parts of a system need to be maintained? Well, we have different components. We have the electrical components, which can have a certain amount of self-monitoring. We have the mechanical components, such as the pipes and the nozzles. Now, the pipes are dry. The nozzles are passive elements. There's no moving parts. So on this part of the system, it is almost maintenance-free. Then we have the electromechanical parts, the valve, which will open or direct the water to the right location to suppress a fire. And this has both electrical and mechanical parts. So we'll show how these can be monitored as well. So the first stage is preventive maintenance. So this is a matter of repairing or replace a part before a fault occurs. Now, this requires a frequency or a periodic inspection and testing to see the status of the equipment, or maybe to replace a part which has a certain lifetime. Just an example of how we can affect this, we have here an illustration of one of the components of a fire suppression system is a flexible hose. Now, these can be made out of rubber or elastomer or metal. Now, elastomer ones will require have a certain lifetime, which means in the lifetime of a train, which may be 30 or 40 years, may have to be changed several times. Whereas a steel or metal flexible hose will last the lifetime usually of the vehicle. Another way of reducing or extending the intervals for preventive maintenance is have a lot of self-monitoring. So electronic components we have in our system will be monitoring, the bus will be monitored, the components will be monitored, and they will actually be able to indicate a fault outside the normal working conditions. Smoke detectors continuously monitor their condition as well as the smoke. And one point which I mentioned was the electromechanical components. Now, here we have an electric motor and a mechanical valve, and we achieve this by having a periodic self-test. So we will send a signal to the valve, which will open and close the valve and test that it fully moves to the end stop and back. As I said, the pipe work is empty normally in normal conditions, so this will not affect any, will not spray any water. There are, of course, some functions which cannot be tested automatically, and these will have to be done in the periodic inspection. For example, smoke detectors, the electronics are self-monitoring, but the smoke chamber has to be tested usually once a year using a test spray, which will spray just to simulate to check that the smoke chamber is working correctly. There are also other components which we cannot really define a fixed interval, such as components which are accessible to the public. So depending on how the public react. Do they is there any interference? Then there may be a visual inspection more frequently or less frequently required. Predictive maintenance is when we have a continuous monitoring for a gradual change in the condition. So if we have for example, smoke detectors will be monitoring for smoke, but they are susceptible, of course, to if there is dust in the atmosphere, this will also be measured. But a smoke detector can distinguish between a continuous build-up of contaminant, slow changes, and rapid change of smoke. But this slow change will first be compensated, but it can be communicated to the control unit, which can then monitor the rate of change. And so it can predict when that contamination level will be so high that it will be necessary to clean or replace that smoke detector, thus avoiding an unscheduled maintenance requirement. In the cylinders, the nitrogen cylinders, they're under pressure. We have pressure sensors, and it is possible to monitor this pressure continuously. So should, in the very rare case that there may be a leak, this could be seen as how long it would be until the pressure would be too low to be ensure a correct suppression, and this will be as predict a time, so it would then give out the information that this should be addressed. And as I say, section valves, the current consumption can be monitored as well with this continuous testing, which will indicate that maybe there is aging, there is something seizing up, and this can be predicted and given the information in advance so that no unscheduled maintenance is then required. There will be at some stage corrective maintenance required, either during normal maintenance cycles, that something has to be replaced or repaired. And the idea of a good design is to make sure that these components can be easily replaced quickly, so the downtime is as low as possible, using connectors instead of fast wiring, using components which can be snapped into rail mountings quickly, or smoke detectors which fit into sockets as opposed to being fixed securely to maybe a ceiling. There's also the event of after a fire has occurred or a water system has been activated, we need to refill the water and nitrogen cylinders. Now, the quickest way of doing this is having it in a cylinder module that we show here, which can just be dismounted from the train, just one electrical connection, one hydraulic connection, and then a new module fitted. It takes a very short time, and the water and nitrogen cylinders can be refilled externally outside the service time of the train. So all these issues on or points on maintainability, the idea of having a good system is to minimize the cost of maintenance. As that we do through this continuous monitoring and inspection, extending the periods if possible, using predictive maintenance, using a good system that can indicate faults, have internal diagnostics, and we provide a dedicated service tool which will help locate any faults and explain what needs to be done. The basis of any system of maintaining it is to keep it a very simple system, less parts, and will keep it the maintainability down. And of course, the most important part is having the choice of all those components designed specifically for the railway industry. And this is what a proper system for railway fire protection system is made out of. So that ends my part on the maintainability. Now I'd like to pass back to Gail, who will go on to the next stage in RAMS, which is the safety.
Thank you, Jonathan, for the valuable contribution, and we will hear you again in some minutes again. Let's speak a bit about safety. And first of all, of course, it's coming from customers' requirement. And here we would like also to point out that sometimes we have different requirements level rising up. This is an example from a specification from a customer asking for a SIL assessment for hardware, software, as well as communication. On the other hand, and I know we have in this meeting room some colleagues from Italy that probably well know the Italian standard UNI 11565, which requests inside only with regard to the release device a safety level of the SIL2. So it means we have seen here discrepancies if we have to do it for the release valve only, or if it is related to the complete system. What's the consequence of this? There is some different requirements level rising up. Sometimes there is some disagreement or discussion aspects between experts and homologation bodies who need to be merged together to achieve a global and common target, which could be possibly a creation of a new standard. We could be hand over all these topics to be merged inside only one standard. What's FOGTEC's approach on this? We decided to go the way to get a fully certified SIL2 hardware and software system, which is a so-called Series 5000. And for those of you who are maybe not so aware about SIL, is a safety integrity level, which mentioned between SIL 0 and SIL 4. And with the FOGTEC solution, we reach until SIL 2 for the complete system. So the Series 5000 we have, it's a really modular solution with a high flexibility to get up to 500 participants on the bus, and with a full redundancy in communication. And you can see on the picture the development time of this solution. We start in 2012 with the basic integrity. Basic integrity BI is for a SIL 0 system, with the first application case starting from 2013. In parallel, we developed the SIL 2 solution, which needs much more longer time, and we get it available from between 2015 and 2016. Having at the end in 2018 the complete SIL 2 assessment. And when we mention SIL 2 assessment, like displayed here, we will speak also in the next slide about all what is required to achieve this as a global complete system. So this is also what we want to point out at this stage. Of course, it's possible to get, let's say, a dummy or an easy SIL system for only relays or only some outputs. But when we speak about system SIL 2, it means that all the parts, electrical, mechanical, all participants to the process needs to be certified for SIL 2, which is what we achieved with our FOGTEC solution Series 5000. We spoke about before what's the request to achieve this target of complete system safety integrity level 2. And there is a really huge documentation amount and validation efforts that are requested. In the first stage, we validate each single components according to applicable norms and standards. Then we go inside the software SIL 2 assessment according to EN 5657. And you can see here on the right an example of all the documents we have to deliver to get the software assessment. And based on this, once hardware and software is validated, we can go inside a complete system assessment according to EN 15129. And this is finally the sole document that the customer will receive. He will get a unique paper saying, okay, FOGTEC solution as proposed in this application case is validated according to SIL 2 for the complete system. But there is a lot of effort and documentation that needs to be provided in the background. Like mentioned by Jonathan before, there is still the right balance to be found between full redundancy and cost-saving LCCs. We have a full redundancy in the activation of the water mist system, electrical and pneumatic. And the balance is on the one side, from a safety point of view, we would like to have as much as possible redundancy in the system to make sure that it is safe. And on the other hand, we will try to reduce the amount of components to reduce maintenance and overall LCC costs. So at the end, there is a right balance between redundancy and cost-saving LCC that needs to be found. At this stage, I will hand over to Jonathan again. He will explain you a bit about lifecycle costs.
Thank you, Gail. On the point of life cycle costs, it's a question of what's it all going to cost. Over the life cycle of a rail vehicle, which is maybe 30 or 40 years, there will be ongoing costs. Now, these are influenced, of course, by the system reliability, the availability, the maintainability, and the safety design, as Gail has just shown. And it may be that a system which has been optimized for the purchase price alone, it may be significantly different in its design for one which takes into account RAMS and LCC. I explained that an example with the hose example was a rubber hose, which may have to be changed several times during the life cycle of the vehicle, will be having an initially lower investment cost to a flexible metal hose. But over the lifetime, with the less maintenance, not needing to replace them, it will in fact give a lower cost than the initial. There may be, in many cases, that over the lifetime of a vehicle, that the life cycle cost can in fact exceed the initial investment if it's not correctly addressed. If it's correctly addressed. So it's always a balance between the initial investment cost and the expected life cycle costs. And by having maybe a higher or a better investment cost to start with, you can in fact reduce the life cycle costs over the whole period. Now, because a fire protection system is often seen as an extra, it's a system that will hopefully never be called upon. It's the cost of a system is very critically observed by the users. And so our intent or our method is always to optimize this, to look to ways to actually reduce the maintenance requirements and keep a safe balance between safety, availability, and this is what's done by a well-designed fire protection system. With that, I'd like to finish the part on life cycle costs and hand back to Gail, who will give you one view of what future developments could be.
Thank you. Yes, we want to finish quite soon this webinar with a futures outline about how can fire protection solution look like in the near future, and especially applied to RAMS and LCC. And what is really important here is to start with an agile system design and software management. If we have the possibility to adapt at the early stage with the raw data to complete system, then it will be possible to have predictive maintenance and to reduce also therefore the overall costs. The overall cost means not only for the car manufacturer, but also for the operator, for a better management of spare parts to make sure that they are anytime available at the right quantity and at the right time and place. This leads for sure at the end to customer satisfaction. But on the other hand, if we achieve to get such an agile software and system design at the early beginning that allows a generic validation of the system, it will be also related to the award documents we mentioned before. If we can achieve to get this generic validation for all application cases, then of course we can strongly reduce the time to market and also reduce the costs, which finally leads to the customer satisfaction. So probably this is the way to go in the near future to adapt fire protection solutions. At this stage, I would like to thank you for your participation. Please follow us on LinkedIn, other social networks, and don't forget to be part of the next webinars that we planned in the upcoming weeks. Stay safe and hopefully see you soon again. Thank you.
Thank you.